Hi, welcome to the Calculus 3 assignment practice series. We are in the unit Vector Calculus. This is our assignment number 5 under the topic, the fundamental theory of the line integrals. And in this video, we're going to practice some of the problems on the assignments. So let you get familiar with the topics we cover in this lecture is a fundamental theory of the line integrals about the conservative field, path independence, those things. Okay, so let's go ahead and get started. Let's take a look at the assignments here. So what type of the problems we are dealing with, okay? Okay, so the first ones here, let's take a look at these problems here. Okay, I like those graphing problem because if you do the graphing problem, it's a very kind of conceptual problem. If you know that, then I think you got a pretty good idea. Okay, so let's say the figure show curve C, and so this is the path and a contour map of a function f here, okay? And whose gradient vector is continuous. So I want to find this integration on these lines here, okay? So I know okay, so if I'm looking for the C, the del F dot drs, right? So for this path here, because the gradient vector is continuous, that means I can what? So I know I can integrate back and find the f of the little f of x. And because I can find it, because this f exists, right? So I know this is what? This is a conservative. If it's a conservative, what's that mean? It's path independent. So that means that this integration will just be the f, right? So will be the f start from the, let me put it like this way, maybe will be better. So by the the path independence, and so this one will be, you start from the path and end at the path, right? So just like we did in the calculus 2 independence, the fundamental theory of calculus, right? So now this will be the end point minus what? Minus the beginning point, right? So let's take a look at the end point, okay? So for this curve here, right? So this is my starting point, right? And this is my ending point. So we know what is the contour plot, right? So contour plot, that's the value of f of x at that point, right? Okay, so now, so that means the f of x, equal to 10. That will be this contour plot. So I know at the end point here, what is my values here? Is 50. Then minus at the beginning, what is here? Is 10. So what is here? So it's 40. All right. Okay. So now let's take a look at the second problem here. Okay. The second problem, I also like this type of problem because it's kind of like the tables, right? And so it's a kind of concept. So let's say a table value of the function f, right? So the table value is my function f here. And f has a continuous gradient. So I know this one's here is what? This one's here is going to be a conservative, right? So if it's a conservative, then that means, it will be what? It will be the path independence here, right? So the t start is 0. Okay, so when the t equal to 0, what is my x here? X is 1, y is what? Y is 0, right? Then when the t equal to 1, what is my x here? X equal to 2. And what is my y here? Y is 2 also, all right? So this is my starting point is 1, 0, and end point is 2, 2. because this is a gradient vector, so I know this is a conservative, right? So now by the path independence, so the df, dr, so what I can say here, I can say, hey, it's because the f of xy functions and the upper bound, the lower bound from the 1, 0 to the 2, 2. The upper bound, the lower bound. So I said f of 2, 2 minus f of what? 1, 0 here, right? So take a look. F of the 2, 2, 2, 2, 2, 2 is what? It's nice, right? And what is 1, 0? 1, 0 is what? It's 3 here. So that's why, so this is a pretty simple problem, right? So it's 9 minus 3 is equal to 6. Okay, so I'm going to, so then the remaining those problems are very, very mechanical, just like we did during the lectures, right? So you take the integration, you take the derivative, and then integrate it back, and then find the functions, okay? Now let's take a look at another, another graphing problem. I like those type of problems here. Like I said before, is because it's a test your concept very well. Okay, so let's say the figure below show a vector field f of xy equal to 2xy and x squared. And we have 3 curves and from the 1, 2 to 3, 2. So this is a curve 1, look like an X here as a curve 2, curve 3. So part A, let's say explain all this integration, right? So this line integral for all these 3 curves have the same value. That means it's path independent. So how do I explain it? So I said, oh, okay, so this is my pxy's, right? This is qxy's here, right? So I say, if I can show this is the conservative, then based on the conservative field, then the path independence. So let's say the rho p, rho y. So what is rho p, rho y is here? Rho p, rho y will be 2x. Then the rho q, rho x equal to what? Is equal to 2x here, right? Okay, so super good. Hey, 2x equal to 2x. So what we said, f is conservative. So the reason why is f is a conservative. And we know a conservative is what? It's a path independent. That's why all these 3 will get the same values here. So now let's say here, say, okay, so if you tell me that is the same value, so what is the value? So we use this problem, try to do our method one more time, right? Okay, so we say the P is here, Q is here. So P, this one also you can say this is a partial X, a partial Y here, right? So I know, so the same ways here, the partial X is equal to the 2xy. So my f of xy is what? My integrating 2xy respect to the dx. So I'm going to have x squared plus what? Plus gy. Now the f of y will just be equal to, you take the partial for y, so x disappears. So you will have what? G prime y. And g prime y, this is equal to the qxy. So the g prime y, qxy is equal to what? Is x squared, right? Okay, so now the gy, what is the gy is here? So you integrate g prime y, right? So the dy. So then the g prime y is x squared dy. I'm integrating to y, so x is a constant, so it's x squared plus what? K. Okay, good. So you plug this one back to this functions, right? So you will find what here? So you will find f of xy is equal to what? You have the f of xy, so the will be equal to the, so it's the x squared, okay? So the f of xy, so I think I did something here. Oh, I missed a y here, that's why. So y squares here, so looks, okay, so now you will have the f of xy will be equal to y square, yx square, gy is what? Gy will be the x squares here, okay? So gy will be x squares here. So hold on, I think I did something. Okay, I guess I know what I'm not careful here. Okay, so here, f prime y. Okay, so that's why I have x squares here. Okay, now you compare to the qxy's here. So now you know the g prime y is what? Is zeros, right? So here, okay, so 9, much better, all right? So that means when you compare, so you know the g prime y equal to zeros here. So you put the zeros here, okay, and then you do the dy. So we know what is the integration of the zeros here. The integration of the zeros will be a constant, right? So constant case here. Now you can plug this one. Finally, yeah, you can plug the gy to, you know, to what we have in here. So that's why the f of xy is yx squared. Much better. Okay, so now I'm doing the integration of the f of the dr. We know this is a conservative field, so I find this function, right? So it will be the path independent. So that means this will be the integration for the f of xy. Then you put your upper bound, lower bound. So it's 3, 2 to the 1, 2. So f of xy is here, right? So it will be yx squared. Then here, this is 3, 2, 1, 2. And then you will find out this answer is 18 minus 2 is 16 here. Okay, so just be careful when you take the derivative, integrate back. So just be careful about the variables here. Okay, so now let's take a look. Okay, so the next ones here, this is also, we practice this one more time here. So what do they want us to do here? They want to find the work done by the force field, moving an object from P to Q. All right, so here, because the work done, we know this is one of the application of the line integral over the vector field, right? So this is my pxy, this is my qxy. Okay, don't get confused with those points. I think that's they put it like not a too good notation there, the PQ points, try to confuse you. Okay, so let's take a look at the rho P, rho Y. What is here? 2xy, 2x plus 1, take it as 1. Oh, good. Rho Q, rho X. Ha, QXY is X, so it's 1. Okay, great. So they are equal. If they are equal, what do we say here? So we say the fxy is what? It's a conservative. Okay, if it's a conservative, that means I can try to find a lower function f of xy. Then I can use the path independence series and then the fundamental theory of line integrals here. Okay, so let's try to do that. So I know the f of x, partial x is pxy. So it's 2x plus y. See here? Now integrate, right? So now I'm integrating here. Okay, so now I can say that f of xy is equal to you integrate 2x plus y. Now integrate for what? dx, right? So it's dx here. So this one's will be x squared plus xy plus what? Plus hy. Okay, and then take the derivative. Lower the partial y, so this will disappear. x will disappear. So xy, the partial derivative x is x plus h prime y. Good job. Then compared to the qxy is x. Oh, beautiful. So what I have here, I have h prime y equal to 0. Now hy will be equal to the h prime y. Take the integration. So this will be the 0, take the dy. So what you have here is a constant, right? Now that's good. So you have this constant. Then plug back the constant to here. So finally, I have my what? I have my f of xy is equal to x squared plus xy plus k. So you can let the k equal to 0. If you let the k equal to 0, then my f of xy is equal to the x squared plus xy. Okay, now the work be done. So we can say this is the integration of the f of xy dr. Okay, and then now because of the fundamental theory of the line integral and the path independent, so we can say this is for the f of xy from which point to which point, 1, 1 to 4, 3. So that means it's x squared plus xy from the 4, 3 and 1, 1. So now you plug it in and it will give you what? 26. Okay, now let's take a look at our last graphing problems here. And so this is not an absolute, it's kind of just test your concept, right? So they say, is the vector field shown in the figure is a conservative? Okay, so if it's a conservative here, let's see here. Let's see with, okay, so if I have a path here, okay. So this is my C path here, right? So if this C go here, it's a closed path here. So if I do this, right? So it's C is going like counterclockwise. Then if you see this C path here, looks like it is all what? It's kind of like it's all kind of the, like it's doing the same directions, right? As the force, that's your vector. So probably for this one here, right? So probably we said, you know, that this work, the work probably is positive. That means this is not conservative, right? So if a conservative, the closed path has to be 0. Okay, now let's take a look at this ones here, right? So if I have some like a smoother curve here, right? C. Now, if I can go this direction, doesn't matter. So let's see here. This direction, this direction, this direction, see this direction. See, it's kind of clockwise. So for this ones here, this one, you know, the potential, have the potential to be conservative. Of course, we eyeball it, kind of feel that way. Because if you go this way, right, some of them going to have negative work, some of them going to have a positive work, right? So, you know, that's why so when you add them, probably will be equal to 0. Right? So for the closed curves here, so this one's here, right? So probably get a close to 0. So this field has the chance to be the conservative field. All right, that's it. So I hope the few problems I did here and help you to get a better understanding about this conservative field and help you to do the other ones here. All the other one remaining is quite mechanical, right? Just try to find that lower f of xy function. Then you can use the path independent and the fundamental theory of the line integral to get the integration results. All right, that's it. Okay, so and hope you have, you know, you'll be able to finish this assignment without any problems, without any the troubles there. Okay, nice to talk to you. And we'll talk about our next topic in the next video. Okay, bye. Have a good day.